Hello, ladies and gentlemen, and welcome back to Prospect Charter School's Algebra 2 class. This is going to be section 1.6, Relations and Functions. Now, the first question we're going to ask ourselves are, what are relations? Well, relations are a pairing of an input in the domain to an output in the range. So let's write that down. A relation is a pairing or a mapping. A pairing or mapping of a set of inputs in something called a domain, set of inputs in the domain to a set of outputs in the range. Set of outputs in the range. Now, an example of this is my personal favorite, Major League Baseball, or MLB. Now, Major League Baseball has a bunch of teams in it, 30-ish. And each team is related to a league. So on the league side, we have the American League and we have the National League. And then on the teams side, we have my personal favorite, the Seattle Mariners, who have never been to a World Series. And with them is the Washington Nationals, who have also never been to a World Series. Nationals. And then there are teams that have been to a World Series too many times, like the Yankees and the Cardinals. And then there are teams that don't go very often or haven't been there for like 100 years, like the Cubs. Or maybe one that hasn't been there in a very long time, like the Tigers. Actually, I think the Tigers have been there recently, but oh well. Anyway, each of these is related to a league. For an example, the Mariners are part of the American League, along with the Yankees and the Tigers. But in the National League, you have the Nationals, the Cardinals, and the Cubs. So looking at this, we have a relation. We have a set of things in the domain. And each thing in the domain is related to something in the range. So the domain would be the teams, the range would be the leagues. Now there's a special kind of relation. This special kind of relation is called a function. A function is a relation where every input has exactly one output. A function is a relation where every input has exactly one output. So let's take a look at our relation over here and determine whether or not it is a function. If we're looking at all of the creatures in the domain, the Mariners, the Nationals, the Yankees, the Cardinals, the Cubs, and the Tigers, every single one of those has exactly one output. The Mariners go only to the American League. The Yankees go only to American League. The Tigers go only to the American League. While the Nationals go only to the National League, the Cardinals go only to the National League, and the Cubs go only to the National League. So looking at that, is this a relation where every input has exactly one output? And the answer to that question is yes. Even though some of them go to the same output, in this case, 3 of them go to the American League and 3 of them go to the National League, that doesn't matter. All that matters is that one input gives you one output. They could all be going to the American League and it would still be a function because every input has exactly one output. It doesn't say one unique output, it just says one output. So let's throw a wrench in the works. Let's throw in the Houston Astros. Now, some of you may know that the Houston Astros were originally part of the National League. But because of there being an imbalance in the number of teams in each division, they decided that they would move the Astros from the National League Central to the American League West. So now the Astros were in two leagues. They were in the National League and the American League in recent memory. So because of this, we now have an input that has two outputs, American League and National League. So is this a function? Agreed, it is not a function because this says every input has exactly one output. No longer do we have an input with exactly one output, we have an input with two outputs, so it breaks it. But if we remove the Astros, once again, we are back to being a function. So let's try another one. Let's try the Prospect Charter School Cougars. Now, the Prospect Charter School Cougars are neither in the American League nor are they in the National League, so they don't have an output in this range. So is this still a function? And the answer is again, no. Every input has to have exactly one output. If I have an input that has no outputs at all, it's no longer a function. It doesn't work. Every input has to have exactly one output. Every input in the domain must have exactly one output for it to be considered a function. So let's go ahead and remove that, and we are back into function land. Now that we know what a function is, a relation where every input has exactly one output, I think I've said that like 10 times now, we can look at a numerical example. Now, in the numerical example, we're going to be looking at the year and then the price of a stamp. So if we're going to be looking at these, I think it would be nice to make another T-chart within a T-chart because that way I can keep things separated. So in the year 1900, the price of a stamp was 2 cents. In the year 1920, the price of a stamp was still 2 cents. Then in 1940, the price increased a whopping 1 cent. And then in 1960, the price again increased by a whopping 1 cent. So from 1900 to 1960, the price of stamps doubled. They went from 2 cents to 4 cents. But then from 1960 to 1980, something awful happened, and the price of the stamp went from 4 cents to 15. And then from 1980 to 2000, it doubled and then some again to become 33 cents. Now, if we're looking at this, is this relation a function? Well, every input is unique, right? 1900 is different from 1920, different from 40, 60, 80, and 2000. And if we look at the price, even though the prices repeat a couple of times, it's still only one price. In 1900, it was 2 cents, period. In 1920, it was 2 cents, period. In 1980, it was 15 cents, period. So in this case, we have a relation where every input has exactly one output. So we can relate functions mathematically. And that's actually one of the beautiful things about functions, is that they can be related in this fashion. And in the next section, we will get to know just how awesome that mathematical relation can be. And once again, I'm going to have to edit this out and see if we can do this, because I really don't like how Windows 8 does that. I don't like how I can do that. It's bad. Okay, restarting. All right, so let's try something different. Let's try putting a relation onto a set of coordinate axes. Way back in the day, in the late 1500s, early 1600s, there's this gentleman by the name of René Descartes. And René Descartes was an awesome guy. Awesome guy. Awesome guy, Descartes. And one of the reasons why he was an awesome guy was because his name was René, but he didn't care. Probably because he was French. Another one was because of the awesome saying that he said, I think, therefore, I am. Which is kind of how we define whether or not something is sentient. If it thinks, it's sentient. If it doesn't think, it isn't. So he was a philosopher, a mathematician, and a scientist. And one of the things that he decided to do was he got really tired of charts. Charts didn't intuitively show you how things were behaving. And he got really, really tired of having to figure things out algebraically when he would rather be able to just look at something for a moment and get it. So what he did is he took two number lines. He took a horizontal number line that he called the x-axis. And he decided to call it the x-axis because, just like me and just about everybody else on the planet, we prefer it if our x's are horizontal, preferably with about 6 feet of dirt on top of them. And then the vertical axis would be the y-axis, because when you ask the question why, you can ascend in knowledge, you can become smarter, you can become more knowledgeable, you can become more powerful, because there is no knowledge that is not in some way power. And the x-axis would represent the input or the domain. And the y-axis would represent the output or the range. And then he would have these things called ordered pairs. And the ordered pairs, which come in the format of x, comma, y, would let you know where on each number line your dot should be. So for an example, 2, comma, 4 would occur at 2 on the x-axis and then 4 on the y. And we put a little dot there, and that would be the point 2, comma, 4. So the beautiful thing about René Descartes' Cartesian coordinate system is that it took something that was not intuitive and turned it into something that is. And that is the very powerful point of graphing, is to be able to take an image and from that image determine what's going on pretty much instantly. It lets us see trends, it lets us see specific examples, it lets us get information and data from a glance rather than having to piecemeal your way through hundreds of pieces of paper trying to determine where exactly on this enormous chart the data that you're looking for is. So one of the things that we need to be able to do with a Cartesian coordinate system is determine at a glance if a graph is a function. So to do that, first steps first, we are going to have to draw a graph. And then once we have the graph drawn, we're going to have to put something on it. For an example, let's say this little squiggly line is our graph. Is this graph a representation of a function? Well, to do that, we need a test. We know that the x's represent inputs. So if I draw a vertical line at each input, that will tell me what the output would be. So if I can draw a vertical line at an input to tell me what the output is, do you think we can create a test that allows me to at a glance know if it's a function or not? Well, we can. It's called the vertical line test. And the vertical line test says that if you can draw a vertical line at any place and it passes through the graph more than once, so passes through the graph more than once, then it is not a function. So look at this guy. Is there any place where I can draw a vertical line that passes through the graph more than once? And the answer to that question is no. So is this a function? Yes, it is indeed a function. So we'll write underneath it, yes, it's a function. All right, now let's erase this graph and let's put a different one. Let's say that this is my graph. Is this graph a function? Well, drawing the VLT over here says, yeah, it is. Drawing the VLT over here, yep, still a function. But what if I draw one right here? How many times does it pass through the graph? Oh, there's one. There's two. Is it a function? Well, it says at any point, right? We found a place that we can, so it must not be a function. This is not a function. So, no, not a function. All right, let's try another one. Let's try one where we have something that looks like this. Is this one a function? Well, it should be painfully obvious. Yeah, it's not a function. All right, that one was too easy. Let's try something harder. Let's try this one. Is this a function? Well, it says if you can draw a vertical line at any place and it passes through the graph more than once, then it is not a function. What does it say about when it doesn't pass through the graph at all? Well, according to the definition of a function, it says a relation where every input has exactly one output. So you would want to say, no, it's not a function. But here's the problem. If we looked at our first relation, if we looked at the MLB one, did we include every single team in the Major League Baseball? No, we didn't. But it was still a function, right? That was because my domain didn't include all the teams that were in both leagues. So let's go back to our current one. In this situation, if I draw a vertical line here, it doesn't touch either of the graphs. So what does that tell you about that x value? Well, to me, it tells me that x value is not in the domain. And if those x values are not in the domain, then every input has exactly one output. And if every input has exactly one output, that means that, yes, this is a function. Okay, now for our last one, this is going to be very similar to a previous one. Hold on a moment. All right, and this one, we're going to have a dot here, going that way, and then an open circle, and then going that way. Is this one a function? Like, Mr. O'Neill, we already did this one. We drew a vertical line right there, and bam, it hit two places. And yes, it did in the previous one. In this one, that little circle thing means that there's nothing there. That you can get infinitely close to it, but never touch, because the thing at the very end doesn't exist. It's not there. So when I draw this vertical line, I'm still only touching it one spot. So this is not a spot. So what does that make this? Yep, it makes it a function. So we'd say yes. All right. There we go. We have seen some of the most ambiguous cases. We have used the vertical line test. We know what a function is. It's a relation where every input has exactly one output. And now it's time for our homework assignment. Don't worry, your homework assignment is really, really hard. Section 1.6, page 47. Numbers 3, 7, 9, 11, 13, 15, 19, 21, 25, 29, 39, and 41. On this one, make sure to show your work. If it tells you to graph something, graph it. If it doesn't, you don't have to graph it. Okay? All right. Good luck and have fun.